Meet the meQuanics is now sponsored by Audible.com. As part of this sponsorship, Audible is offering a free audiobook download with a 30-day trial so you can check out the range of titles that they're offering. Currently, Audible has over 180,000 books to choose from for either your iPhone, Android, Kindle, or MP3 player. To help support this podcast, please go to www.audibletrial.com/meQuanics. And now, on with our next episode. Okay, thanks again everyone for joining us. This is another sit-down offline episode of Meet the meQuanics. We're sitting here at a coffee shop at Recon, and luckily I have Jake Taylor sitting next to me from the University of Maryland and the Joint Quantum Institute. He's been visiting Tokyo now for, 3 months?
2 months.
2 months. And so finally we've had a bit of a chance to sit down and have a chat over coffee about what Jake's doing and what's happening on the east coast of the US. So Jake, thanks for sitting down.
It's a pleasure to be here, Simon.
So generally I usually start these things off as to give us a bit of a background to yourself and what do you do and what does your institute do. From what you've said, the Joint Quantum Institute and the University of Maryland are actually two separate institutes, is that right?
So I work for the National Institute of Standards and Technology, which is based in Gaithersburg, Maryland. And NIST, as we call it, has a pretty strong effort to try and understand quantum devices and quantum information technologies. And as part of that large effort, we have a joint institute with the University of Maryland called the Joint Quantum Institute, which was founded back in 2007 and is dedicated to the study of quantum phenomena. In addition, we recently began the Joint Center for Quantum Information and Computer Science, which is also a collaboration between NIST and the University of Maryland. But rather than being physics-oriented, it's more computer science-oriented. And I'm involved in both of these efforts. So I guess you could say that it's several different groupings of quantum information researchers that are all physically co-located on the University of Maryland campus. And we're dedicated to the proposition that quantum things are interesting to understand. We don't understand them as well as we should. And by understanding them better, we might push forward what you can compute.
So, I mean, your publication record's quite rich. You're a theorist, obviously, but you seem to be all over the place. You do all kinds of bits and pieces. I'm not sure I could say you're a condensed matter theorist or an optical theorist. You seem to dabble in everything.
Well, I prefer to think I don't dabble. No, but to say it in other words, I focus on the interface between quantum information ideas and devices that try and implement them. Because the devices that people are working with work in a variety of different physical regimes, from cryogenic, semiconducting, and superconducting experiments up to cold atom experiments, into room temperature mechanical systems, into optical systems operating at 200 terahertz, it requires a certain amount of breadth of understanding in order to see how the different pieces fit together. And so, in that sense, I have the benefit of spanning or spreading over multiple different subfields in the broader context of quantum information.
Mm-hmm. So, I mean, what's your focus at the moment? I suppose, what's your favorite little piece of quantum devices, quantum mechanics that you're focusing on the last 3 or 4 months?
Well, I have a few different efforts that have been consuming most of my time in the last period. One of the most interesting to me is asking how can we build mechanical systems, so big chunks of stuff, in such a way that the mechanics behave fundamentally quantum mechanically and might hopefully produce a frisson with our current understanding of gravity. So this conceptually is trying to focus on the idea of macroscopicity, which is that quantum things, when they get bigger, might become more susceptible to decoherence. And decoherence is the main mechanism we think about for a quantum system to essentially go classical, as this information gets leaked out to the wider world. There's been a tremendous improvement in mechanical systems over the last 15 years, to the point that several groups around the world have now cooled such systems to their nominal quantum mechanical ground state. And these are systems that are in this sort of nanogram range, which sounds like not very much mass. But that's to be contrasted with the first systems that were successfully cooled mechanically to the ground state, which would be single ions in an ion trap. And so the progress from 10 to the minus 21 grams to 10 to the minus 9 grams, so a trillion and a factor of mass, has been tremendous. There's now hope on the horizon that we can go from nanograms to milligrams, another factor of 10 to the 6. And now you're starting to look at the prospect that there will be quantum mechanical superpositions of objects whose mass is comparable to the Planck mass, which is at 21 milligrams, whose superposition lifetime may be hundreds to thousands to millions of mechanical oscillation periods.
So what does this mean in sort of from the layperson's perspective when you're talking about cooling something to its quantum mechanical ground state, and you're trying to build big objects that vibrate in different superpositions, are physically in different places at once? I mean, is this really trying to build sort of, a Schrodinger's cat, just not with something alive?
It is trying to build the Schrodinger's cat, and there have been some great successes using the same mathematical concepts, but not doing it with massive objects, but by doing it with light, particularly from the group in Yale, where they've been stabilizing, and they recently showed a pioneering advance in which they took a cat state in what's called a cat state code. So it was actually not just one cat state, it was like two cat states put together, patched together in such a way that it would be correctable if errors occurred. And then they corrected it. And so you can stabilize and correct using quantum optical techniques highly entangled states of light, and mathematically, light is a boson. And mechanical oscillations of an object, which we call phonons, are also bosons. So in principle, the same techniques that operate for the superconducting optical community, by optics here we mean microwaves, should also be applicable to the mechanical systems. And then you could ask, how long can I stabilize these mechanical superpositions using these concepts? And now one of the big differences is that light is very light, if you pardon the phrase. And so the impact of light on, for example, other objects around it via gravitational interaction is exceedingly weak. When we start to move to more massive objects, something that goes from essentially unobservably small to something that might be observably small becomes a possibility, let's say. So that's why I've been so intrigued by it. Now, it's not just about testing large mass superpositions for the sake of testing large mass superpositions. These same mechanical systems have immediate application in quantum information science. And we've been looking there at two different application spaces. So one is what's called quantum transduction. You have spent huge effort, millions of dollars and tens of graduate student years, building a wonderful superconducting quantum computer, sitting in the bottom of your dilution refrigerator at 10 millikelvin. And now you might want to ask the question, how do I network this quantum computer with another quantum computer that's not in the same dilution refrigerator? Maybe it's down the hall. Maybe it's on a campus across the city. Maybe it's on the other coast of a continent. And to do that, we need to develop some understanding of quantum networking and how we distribute entanglement between quantum devices. One thing that we can understand pretty well is that of the different possible ways to move quantum information around, optical photons, light, remains one of the best. The problem is that superconducting devices are not playing very nicely with light. When a light photon hits a superconductor, it creates quasiparticles, it destroys the local superconducting order. Now, this has been wonderful for people who want to accurately detect single photons. These are the cutting-edge single photon detectors. But it's not so good for the quantum information perspective. So we'd like to come up with a way to take those microwave signals that represent the quantum information stored in these superconducting qubits and move them up to the optical domain. We can't do it with the amplifiers, because if we take quantum information and we amplify it, we have effectively measured it and added noise in the process.
Yeah, this is related to this no cloning that people have talked about before, isn't it? That you can't,
There is no
you can't copy a quantum
correct.
state.
That is correct. I can't amplify without noise, because it corresponds, if I could, it would correspond to cloning the quantum state.
Mm-hmm.
So you'd like to come up with a way that doesn't involve amplification. So you can't just attack the problem like you would sending information through the internet, where you have fiber optic cables and amplifiers that amplify the signals. So a long time ago, we identified, us and many others, identified several different approaches for dealing with this problem, which tended to be lumped under this larger category called quantum repeaters. But at the present time, I'm more interested not in how you get the photons from A to B, but how you get the microwave signal up to the optical domain in the first place. And here the mechanical systems can play a starring role, because electronics couples to mechanics through a variety of mechanisms, but anyone who's used a speaker or a microphone understands that an electronic signal can make sound, and vice versa. At the same time, when a mechanical thing starts moving, light, when the light bounces off of it, is shifted. You get two different effects. You get a Doppler shift, but you also get the generation of sidebands. You have the possibility that light from an incoming laser, for example, is frequency converted with the addition or subtraction of one photon to a new photon at a different frequency. These sort of so-called sidebands are a way to take a microwave signal, move it into the mechanical degree of freedom, essentially making a
vibration of it.
Well, we call it a mechanical loudspeaker. It's not so loud, actually. It's at a single photon level. But
well, that's what I was going to ask, is that these things, these measurements must be so small. I mean, you're talking about single phonons, single quantas of vibrations that you're changing things by, and they're conceivable that you can measure something this small?
Well, it's not only conceivable, it's been done. So, in particular, these excitations are very, very small, but the thing about the mechanical systems is that the excitations last an exceedingly long time. And so you have the opportunity to let the attempted conversion, where the microwave signal comes in, becomes a mechanical signal for a period of time, and then is converted up to the optical. You can take your time doing it. And by taking your time, you can offset the weakness. So, at the simplest level, this would provide a sort of lossless pass-through of the electrical information up to the optical domain. And it's now been demonstrated by two groups with, albeit pretty small quantum efficiencies in the sort of 1 to 10% range.
Mm-hmm.
But it's actually astonishing that they're able to take single microwave photons, convert them up to the optical domain, and still get 10% of them coming out quantum mechanically. So anyway, this has been one main source of effort and interest for me. The other one is more related to the fact that I work at the National Institute of Standards and Technology. And that's been asking, how do we use these quantum information effects to make better metrology standards? Now, quantum information, you think about information processing, but you're often limited by your ability to actually measure things.
Mm-hmm. Mm-hmm.
When we talk about quantum limited metrology, we're talking about measuring things at the very limits of what quantum mechanics allows. But there's another sort of strategy, which isn't trying to get to the limits of quantum mechanics in respect to how well you can measure, but rather to use quantum effects as a way to move between the microscopic domain, where we use natural units sometimes, where we have Planck's constant and the Bohr radius and the electron charge, to terrestrial scales, where we have the coulombs of charge, which is million trillion of electrons and kilograms of mass,
Right.
and things of this nature. So to go back and forth between them, when we want to make a standard, it has to be something that someone in industry can go use. Right? If you want to make a standard for in our particular case, we're looking at temperature, right? It should be something that reads out. Well, I guess we're here in Japan right now, so reads out 30 degrees centigrade.
Oh, rather than Fahrenheit.
Well, maybe today more like 25.
Yeah.
But,
Well, actually, we had Jared on the podcast a while ago. He actually made a very good analogy. Would be, how do you explain Kelvin or centimeters or a second to an alien race when you can't send them anything except
right.
communications.
So in some sense, as part of the redefinition of the SI, the system of units that we use, we're trying to move towards using fundamental constants wherever possible. So in particular, in temperature measurements, it's very challenging to do this for two different reasons. One is that temperature is not a local microscopic quantity. Temperature, as a theorist, I say temperature is a Lagrange multiplier, but no one really understands that. But no, it's an aggregated property of an average system. And so you can't really measure temperature. You have to measure heat load instead. And so when we want to do quantum thermometry, we need a way to convert between some energy and something else. So if we do dimension analysis, this is a physicist's favorite, we know that to get from temperature to energy, we use the Boltzmann constant. We can't measure energy that easily, but we can measure frequency. To get from energy to frequency, use the Planck constant. So now, in principle, if we can make a frequency measurement, we might be able to convert it to a temperature measurement, if only we found the right system. So what we've been looking at is using the random thermal motion of these mechanical oscillators as the way to determine this relationship. This is called Brownian motion. And what's amazing is that we can use the quantum part of the noise. This thermal noise has a classical contribution representing thermal stuff and a quantum contribution. And the quantum part can actually be used to calibrate the size of the classical part to directly determine a unitless quantity that's equal to this temperature to frequency ratio. And so this allows us to make a primary thermometer, which operates in a huge range as primary thermometers go. It goes, roughly speaking, from 4 degrees Kelvin up to 300 degrees Kelvin, so from near absolute zero up to room temperature. And so we think this is a really interesting way to use quantum effects to make a better standard. So these are some examples of why these mechanical systems have some immediate impact, in addition to my maybe larger scale questions we can learn about the universe from them.
You mentioned something about these systems being used for investigations of gravity. How would you go about that, considering that we're trying to investigate something that operates on such large scales with a device that's fundamentally tiny?
Well, there's been a lot of ink shed on this topic. So there's a few different hopes for trying to understand something about gravity in terrestrial experiments on Earth. And they relate to some interesting observations. So one observation is that the Planck mass is around 21 milligrams, which is not actually that much mass. So, you have a...
So maybe explain what the idea of the Planck mass is. Is it...
Well, if you're familiar with Einstein's concept of relativity, that energy and mass are interconnected, then you can get to a point where the energy density of a chunk of stuff is high enough that it would cause space-time to curve an appreciable amount. And if you look at the length scale of which this energy would have to sit within, then you get a mass scale, which is called the Planck mass. And this Planck mass is very large from a high energy physics perspective,
yes.
but very small from someone who's trying to keep track of their weight and while they're eating their diet perspective. So one of the hopes that these experiments might have something meaningful to say is simply that the mass scales are starting to become appreciable to scales where gravity and Planck's constant are playing together. Because the whole point of the Planck scale is defined in terms of Newton's gravitational constant and the speed of light and Planck's constant. So there's just kind of the point where h bar and g play together. And one of the other interesting things has been the realization that on relatively short length scales, we don't really know what happens to Newton's laws of gravitation. And so there's a bunch of speculative concepts people have suggested that will help try and deal with other problems about gravity that we don't fully understand, where if you could test gravity in the range of 1 to 100 micrometers, you might learn something new. And so these are systems which you need to get pretty small, and you need to be able to measure them extremely well. And these mechanical systems have to be in a good spot for that.
So this is really about trying to to investigate gravity in the regions where people think that gravity and quantum mechanics aren't going to play nice together.
Well,
But there is a contradiction.
let's say the optimists
The optimists.
think that they won't play nice together. Unfortunately, there's about 17 orders of magnitude from the optimists to the pessimists. So one has to, keep one's bets hedged. Our particular example has been trying to understand what the quantum channel capacity of gravity is. So what's the possibility for gravity to entangle things? So we have some efforts towards that regard, but I think it's a bit technical at the current. So that's one area that I've been focusing on and very interested in. And I just want to mention the other one. So these are the two main things I'm doing while I'm here in Tokyo.
Yeah.
Right. So the other one that I've been very interested in is the question of quantum simulation. And the reason I'm so interested in quantum simulation, of course, is that we have a bunch of things that we use in our daily life, primarily from the biomedical industry, where the knowledge of that thing, how we built the drug, how we built the material, depends upon our classical ability to efficiently simulate quantum mechanics. Now we know that this is not a winning strategy overall. Quantum mechanical systems become exponentially hard. However, we've had some remarkable successes in finding stupidly good approximations. And probably the most famous of these is this field called density functional theory, which the two most cited papers in physics are density functional theory and density functional theory. And basically, density functional theory is a way to try and solve the many electron problem, which is generically very hard, using a variational principle. Using a principle where you can use underlying mathematical principles to tell you that if you get close, you're doing better. And it works really, really well for reasons that we don't fully understand. But you always have to make a guess as to what this functional is. And there's a whole library of different functionals that people don't know why they work. So now imagine that you're armed with a quantum simulator, a device that lets you controllably run the quantum mechanics, which you can then compare against your classical computer. And that allows you to do a classical quantum co-design, where you take your quantum thing, use it to test your classical algorithm, improve your classical algorithm, use the quantum thing to test again, and that may take us into a new regime with respect to classical simulation of quantum systems. As we try and build quantum systems, they become so hard to understand that there is no classical theory for them. And when I say classical theory, I don't mean this in a physicist sense. I don't mean this in a philosopher sense. I mean this in a computer scientist sense. Is the simulation of the theory only polynomially harder than the actual physical system?
Yep.
And then it would be a classical theory in the computational complexity sense. So, of course, this interplay between computational complexity and our concepts in physics is an area of great interest, and there's a lot of fun things happening there. But perhaps we won't go into those details at the present.
No, because I mean, this sort of leaps quite well into the next part that I was going to ask you about, namely the progression of quantum information technology. So quantum computers, quantum communication systems, sensors. We've seen a kind of bit of an explosion over the last 2 years when it comes to investment in terms of technology development. In terms of the work more specifically being done in Maryland and at NIST and sort of globally, especially when it comes to things that you're interested in, whether it's quantum simulation or these micromechanical things, how do you see the technology side of this sector moving compared to, say, the academic side? Is it starting to shift? Is it moving more into this space, or do you still think no, it's going to sit around in academia for a little bit longer?
Well, as you may have guessed, I'm neither an entrepreneur nor a businessman. So I can't speak to what would motivate a business directly to get into this field or not. I can say that as we understand quantum systems better, opportunities start to emerge where there's things that a quantum system can do that you basically just can't do classically. And as that knowledge grows, the possibility to build devices that someone wants to buy to do those things goes from zero to non-zero. But where the killer apps are remains honestly murky. Because the difference between a great idea and a great idea that sells is large.
Yeah.
So, that being said, there are several companies now working on quantum information derived technologies. Be they attempts to build computing facilities that do quantum annealing or related concepts, be they sensors that work at the limits quantum mechanics essentially imposes upon us and then tries to do as well as we can relative to those limits. You know, within NIST, we don't build devices to sell them. We do science for the sake of the country, and as part of that effort, for example, we spent a lot of time working on Tomic Locks. So Tomic Locks are in some sense one of the oldest quantum information technologies, but they're in widespread use, and anyone who's ever used a global positioning system,
which is everyone
to know
now,
where they are right now and which subway line to get on, they used atomic clocks to do it. And it's been, so that's a very large part of our effort, our continuing effort at NIST. We also have a more recent effort, which is to make a random number beacon. So the only randomness that we really know that we can certify as random is quantum randomness. And how do we certify it? Well, we use Bell's inequality. We use essentially a CHSH type game. But the point is that Bell's inequality gives you certifiable randomness between two parties. And if you want to build good cryptographic keys, for example, or if you want to test your cryptographic protocols against appropriate levels of randomness, you need random numbers that you know are random.
or build poker machines for Vegas.
I can't speak to that.
I've heard that they're the largest customer so far of ID Quantique's random number generators.
That could be. That could be. That's again a question of business versus what's practical versus what's possible. But you know, the point is that these are immediate examples of things where, at NIST, for example, not me, but my colleagues did this wonderful experiment violating Bell's inequality, contemporaneous with one perhaps you heard about from the Delft group, but then.
Well, Stephanie did a podcast with us a couple of weeks ago talking about what they did. So
yes.
NIST did a similar experiment.
Well, NIST didn't use a quantum memory to get rid of the loopholes. It was actually, but this is the testbed system for a random number generator, and so our requirements were we had to have much higher confidence in the results than the memory-based approaches could achieve, and we needed much higher rates in order to be able to serve many potential customers for this type of random number beacon. You know, NIST at the present time is responsible, for example, for network time, right? So that's a service that is provided in a similar way you can imagine random numbers being a service provided. So suffice to say, the crucial point here is that you need a very high confidence and a high bit rate. So the experiment couldn't use memories because memories required too long. They had to beat the loopholes by using great detectors and by building the setup with just the right angles so that everything lined up. And so they were able to do it. But this is an example of how you do a quantum information experiment. I want to violate Bell's inequality without loopholes, and you also realize there's a technological benefit to it. Like now I can certify random numbers. So I think that this type of thing is going to keep happening. Is there going to be an explosion in the next year where all the sorts of startups take over? Well, I don't see it happening personally. But I'm not a venture capitalist.
Sure.
I'm not an entrepreneur. So I can't say.
Well, I mean, the last thing I generally ask people is for their predictions. You know, I've got a good bottle of whiskey of your choice up for grabs for anyone I can come back to in the next 5 years and figure out who came the closest as to where you think, you know, quantum computing and quantum information in general. What new things do you think the general? Yeah. So what we were talking about. Oh yes, a possible prediction. What do you think is going to happen in the next 5 years in terms of the general public? What is the general public going to see as sort of as the front for quantum computing or quantum information technology?
Well, what we're seeing right now already is this pretty strong interplay between attempts to build quantum devices to solve information challenges, for example, in annealing and satisfiability, and then improvements in classical algorithms to solve the same problem. We're going to see a lot more of that. I already outlined a scenario in density functional theory, for example, where this is going to start happening. And the consequences of that for the layperson may not be that apparent, but maybe you'll get a better route when you ask Google Maps to go from A to B. So I think another area that you're going to see a substantial more happening in is going to be in the domain of cryptography, and it's going to come in two different categories. Right? And one category is going to be efforts to integrate quantum key distribution systems into existing infrastructure, where you may find that people will start advertising that they're using quantum key distribution for their security purposes. But I think the other area you're going to see quite a lot of activity in is in the field of what's called post-quantum cryptography. Post-quantum cryptography is not postmodernism. It is asking the question, how do you accomplish the day-to-day cryptographic tasks that we use for e-commerce, for our email, for our WhatsApp, for whatever it is? How do we accomplish those in a world where some fraction of potential adversaries and eavesdroppers have access to quantum resources? And there are a bunch of cryptographic protocols that we don't even know how secure they are with respect to a quantum attack. And we don't know how secureable they are with respect to a quantum attack. And so I think you're going to see changes at the infrastructure level over the course of the next 5 to 10 years where the push is going to really be towards adoption of post-quantum standards, if only we know what they are. So those are the things I think the layperson is going to hear the most about. The other thing that those who are maybe tuning into the scientific podcasts are going to hear more of is the interplay between high energy theory and quantum information theory. Because it's just been exploding in the last 2 years, where high energy theorists, people who work on string theory, who work on loop quantum gravity, are realizing that some of the challenges they've been running through in their theories are ones that are actually best understood from the framework of quantum information. And they haven't necessarily thought as much about the information content of the theories. And so I suspect you're going to see many more popular articles talking about about the information of the universe and the surfaces of black holes. And okay, I'm not a reporter, so I can't come up with good poetic turns of phrases that represent the key point in a paper, but you can imagine that you're going to see a substantial change in these understandings and descriptions about what we think the universe is and why it is. And I think that's going to be driven by quantum information, and you may not call it technology because it looks like it's math. But, do you call an algorithm technology?
No, I mean, as most people will be fairly aware, all of the bigger questions and the more speculative questions drive development.
That's right.
Certainly at the lower level. So finally, before we close up and we get another coffee before we leave, anything you want to plug, anything happening at the university or at NIST that you want to point out?
For those of you who are coming to QCrypt in September, so we're hosting QCrypt at CRICS. CRICS is the Joint Center for Quantum Information and Computer Science, where I sit. And we're hosting QCrypt 2016, so this is the biggest quantum cryptography conference, and it's the first time in the United States, so we're very excited to have it.
Yes, last year was here in Tokyo.
So for those coming, welcome. And for those of you who are looking at this and listening to this and you're at the postdoctoral level or at the doctoral level, we have an annual competition at both the JQI and at QUICS for the best postdoctoral fellows. And we highly encourage you to apply because we'd love to have the best and the brightest working on these problems.
Great. Well, I mean, as usual, I'll put links to the websites and all this information that Jake has available online with the descriptions of this podcast. But thanks again for those of you who have tuned in, and thanks, Jake, for taking the time and talking with me.
It's a great pleasure, Simon.
Great.
Take care.
Cheers. Well, thanks for that.